Good afternoon, ladies and gentlemen, and welcome to the final year presentation for the ESMO project, the European Student Moon Orbiter. And I just request one of our team members to operate the slideshow, please. Thank you very much. Now, the ESMO project is a project run entirely by students across 19 different universities in the whole of Europe, consisting of 23 different university teams. Now, the project is managed. We'll go into what we're doing first. So, our part of the satellite is the EPS, or the electrical power system. So we've got these solar panels here. We've got the battery, which you can't quite see on this picture, and we've also got the central power conditioning and distribution unit, which is right back there. We're going into quite some detail into these elements, so we'll try and keep it interesting, but it'll be quite technical as well, so try and follow along. So this project was initiated by ESA back in 2006. As I already mentioned, 23 student teams, and the projected launch date is going to be 2014, according to the current schedule. Now, it's been managed at SST by Surrey Satellite Technology since 2009. So we've essentially been running to a set of milestones set by them since 2009. Just to briefly outline the roles of our team, we have 4 mechanical members and 4 electrical members. We have Mark, James, Will and Andre, who work on the electrical parts of the EPS, and we have Felicity, Louise, Adam, myself, and Ollie, who work on the mechanical elements. We also have non-technical roles, which include finance, health and safety, sponsorship, publicity, and inter-team communication management. So, the milestones of the project are set out as follows. We're currently in the PDR phase, and currently they're holding what's called the PDR co-location meeting, which is where they take all of the documentation we provided for them, all the documentation that other teams provided for them, get together in a big room and discuss it and find out whether we can actually proceed as planned, which is what we hope is going to happen. Just to give you a brief overview into the financial side of the project, we are currently, it's quite a low budget project, as you may have gathered. But we are accumulating money throughout the years as we go, because we know that in the prototyping stage of the project and in future years, teams will need a larger budget in order to produce components, real space-grade components, in addition to the sponsorship that we get. So, just to give you a quick outline of the system. This diagram you'll see on every front cover slide to each section throughout the slideshow. It gives you a quick overview of what is involved in the EPS. So, on this diagram, the red lines indicate power, and the green lines indicate data flow. So, we'll go into some more detail. I won't describe this diagram in any detail here, but we'll be learning more about it as the presentation goes on. So, without further ado, let's hand over to Felicity Kendrick, who will be talking about thermal analysis of the solar arrays.
ESMO will be powered by 2 body-mounted solar arrays positioned at a 90-degree angle to each other. The EPS team has several challenges to face in terms of the mechanical design of the solar arrays. We must consider thermal cycling as the satellite enters and leaves an eclipse. Secondly, the arrays will be bombarded by high-energy radiation and damaging charged particles from the sun and space. Finally, the arrays are vulnerable to high stresses as a result of vibration during deployment and launch and deployment. In light of these challenges, the design as it stands is represented by the layered figure on the screen. The mechanical strength is given by the solar panel substrate, which consists of a layer of aluminium honeycomb sandwiched between 2 layers of carbon fibre reinforced polymer. The aluminium honeycomb is suitable as it is light whilst having a high specific stiffness in this direction. The sandwich effect provides resistance to bending, and a layer of polyamide film, shown here, is necessary for providing electrical insulation between the solar cells and the carbon fibres. The solar cell assembly, represented by the top 2 layers, will now be discussed by Louise.
ESMO will be powered by triple junction solar cells, which have a nominal efficiency of 28%. This is significantly better than the standard silicon solar cells, which typically achieve 15% efficiency. Solar cells produce power over a range of voltages and currents, as shown by this plot, which is the IV, or current voltage curve, for the cell that ESMO will use. The extremes of the graph are the short circuit current in the top left and the open circuit voltage in the bottom right. Between these two, There is a point of maximum power output, power being the product of current and voltage. Below the maximum power point voltage, the cell operates at an approximately constant current. Above the maximum power point, the current drops off sharply to zero. 256 of these cells will be arranged over 2 panels with a total area of about 1 metre squared. They'll be connected as 16 strings, each string having 8 cells in series. This configuration will produce about 19 volts at the maximum power point, although this is dependent on temperature and the age of the solar cells. The power produced will similarly range from 190 watts to 250 watts over the temperature range over which the cells are expected to operate. This graph shows the variation in power output, voltage and efficiency over the temperature range of the cells. This is one reason why it's necessary to produce a thermal model of the solar cell's behaviour. The second reason is that changes in temperature will induce stress cycles in the solar panel substrate, which could lead to fatigue damage over the life of the solar panels. 3 main types of heat transfer were considered in the modelling process. Solar radiation, radiative exchange between the panels and the rest of the spacecraft and between the panels and the space itself, and conduction through fixing bolts and electrical connections. In order to model these processes, 3 different approaches were used. The first was a lump system analysis, which considered the panel as a homogeneous thermal mass covered in the skin with surface properties of absorptivity and emissivity. An energy balance led to a differential equation which was solved using a forward Euler method, and calculations showed that the effect of conduction through the bolts to and from the rest of the satellite is small. In order to validate this initial model, the thermal behaviour of the panels was simulated using a CFD program, SolidWorks Flow Simulation, which has the capability to model radiation and conduction-only situations like those of space. A structural model was produced by simplifying various aspects of the panel geometry. The panel was then modelled in isolation and in radiative exchange with a second surface, which was going to represent the rest of the satellite, shown by the grey plate in the animation. Because the structure of the rest of the satellite is not yet known in any great detail, this simplification was the best we could do for the moment. I'll now hand over to Felicity, who will explain the third model.
As solar radiation is incident on the front of the panel, the absorbed heat flux is constant over the surface, meaning that heat is dissipated through the layers and conduction is approximately one-dimensional. Based on this reasoning, a 1D thermal model was developed and solved using a Fortran 90 program. The image on the screen shows an expanded view of the layers within the panel. Within the layers, the heat equation was solved, and on the surfaces and between the layers, various boundary conditions were applied. Q1 and Q2 represent the heat flux absorbed by the cover glasses and the solar cells, respectively. Without going into detail, the model was solved using the forward time centered space method, meaning that a forward Euler method was used for the time derivatives and the spatial derivatives were approximated using central differences. The graph on the screen shows the solar panel heating on leaving an eclipse, with the various coloured lines showing the different modelling approaches that have been discussed. The 1D model, represented by the top 2 lines, has an obvious disadvantage in that it assumes that the solar panels are entirely covered in cells, whereas in reality the exposed polyimide film between the cells will reflect radiation. The SolidWorks model and the lumped model were improved by considering the effect of the rest of the structure by incorporating a backplate and a view factor respectively. A similar graph shows a solar panel cooling down on entering an eclipse, and as you can see there is good agreement between the results of different modelling methodologies. I will now hand over to Mark to talk about the battery.
Thank you. So I've seen that in sunlight the satellite is given power by the solar rays. However, in periods of eclipse, there needs to be a secondary power source, and this is a lithium-ion battery. Now, we use a lithium-ion battery because it has very good space heritage, shown there. It also has a high density compared to other technologies, high power density, which means that for the same size battery you get more power, or you can have a smaller battery to get the same amount of power. It also has no memory issues, which means that you don't have to discharge it every now and again to keep its full capacity. The cells we'll be using are the ABSL 18650 lithium-ion hydrocarbon cells. The important parameters are listed in this table here. The ones to notice are the voltage range, 2.5 volts to 4.2 volts, which you must stay within. The capacity of 1.5 amp hours, which means that the cell can deliver 1.5 amps to a load for an hour. And also the maximum and minimum, the maximum charge current and discharge current, as well as the temperature limitations. The battery will be made up of 80 of these cells, arranged in an 8S10P configuration, which means that there's going to be 10 parallel strings of 8 cells each. And from the cell characteristics you can extrapolate the battery characteristics. Again, the important ones to notice are the maximum voltage and the minimum voltage. You must stay within this range. The capacity is now 15 amp hours, which determines how much power the satellite can use during eclipse. When using lithium-ion battery in a powered system, you need to make sure you do the battery management correctly. The most important being, you must not overcharge the battery. If you do, you'll permanently damage the battery and it can possibly explode, especially at high temperatures. Also, you mustn't discharge the battery below its minimum voltage, which will also damage the battery. To do this, to make sure you don't overcharge the battery, use the constant current, constant voltage charge algorithm, which is shown here. The constant current phase, to begin with, charges the battery at a constant current until the battery reaches its maximum charge voltage. You then begin to ramp down the current whilst keeping the charge voltage at its maximum, thus you don't overcharge the battery. Another thing to consider is capacity fade. When you start to charge and discharge a lithium-ion battery, its capacity will fade from its maximum, as shown by this graph here. This shows the testing period and the actual mission itself lasting around about a year. From this graph, we can see that the battery charges by about 22%, leaving 11.7 amp hours of capacity at the end of life. If you factor in a string failure, this will mean that the end of life capacity is 10 amp hours, which is considerably less than we started with. To make sure that we can actually deliver the amount of power that the satellite needs during eclipse, we've decided to make a simulation model of the battery. I'll now hand over to Andre, who will discuss the simulation model.
Well, SSTL have provided us with the mission's power profiles and has suggested that an AS10P battery model should be used for our mission. In order to verify this, the EPS team have created a battery simulation model using MATLAB and Simulink. The MATLAB Simulink model is shown here, where the three main components are the charging battery model, discharging battery model, and the thermal model. The model generates typical data for the ABSL 18650 lithium-ion cell, which is used for the battery pack. The steps taken in creating the model are in gathering empirical data for the battery and extracting patterns contained in this data and storing them into Simulink lookup tables, which is shown in step 2. Though there are many equivalent battery circuit models used for modeling batteries, the one used for our model is the Fedinian circuit model, which is shown here. And the transfer function is derived from this circuit in order to implement it into Simulink. The final step in the battery model is to validate it. And in order to validate it, we have used BEAST, which stands for Battery Electrical Analysis Software Tool, which is used by ABSL and was developed by ABSL in order to generate empirical data for this typical lithium-ion cell. We can see that BEAST shown in blue and the Simulink model shown in red are similar. For the battery thermal model, a general equation was derived for the cell's temperature while discharging, which is shown here, and during rest and during charging. A thermal network was implemented. Again, the thermal model was validated with BEAST, and the BEAST data is shown in blue, and in red is our Simulink data. Here is we're showing how you would implement a coded circuit model in Simulink, and how a general equation with 3 lookup tables here containing the key values stored in the Simulink lookup tables. These are the three power profiles provided by SSTL. We then insert each power profile into our Simulink